Hello, this talk is about SymPiece, a novel approach for highly accurate piecewise linear approximation through similar segment merging, a work by Xenophon Kytios, Panagiotis Lakos, Katia Papakonstantinou, and Yannis Kotivis, all affiliated with the Athens University of Economics and Business. Contemporary applications generate massive amounts of streaming data, often depicted as series of time-stamped records. Due to their volume, applying compression techniques is necessary as a means to reduce the respective storage requirements. Depending on the problem at hand, one could use either lossless or lossy compression, and there exist time series management systems like ModularDB that use both kinds of techniques to maintain data values within a user-defined error bound that could be possibly set to 0. Piecewise linear approximation is a fundamental data compression problem dating back to the 60s that is commonly used to approximate time series data. PLA algorithms represent time series measurements using a sequence of line segments while keeping the approximation error within a predetermined acceptable threshold. Clearly, these algorithms are associated with a trade-off between space efficiency and precision loss. PMCMR is an example of piecewise constant approximation. Swing is a PLA algorithm that uses joint segments. Slide provides the optimal representation when using disjoint segments. And mixed provides improved space efficiency by using a mixed representation with both joint and disjoint segments. ModularDB uses the Gorilla algorithm for lossless representation and uses either PMCMR or Swing to allow users to set an error threshold and acquire space savings. Now, in many applications, such as the ones using sensor temperature measurements, there is a certain amount of imprecision in the collected data, and there exist lossless techniques such as CIMP, that was proposed in last year's conference by our group, that provide better space efficiency than lossy techniques. In the figure, we see that CIMP needs less space than the PLA approaches discussed earlier, when the desired error threshold is set at 0.5% of the signal's range. If we set the error threshold at 5% of the signal's range, we see that the PLA approaches offer better space savings than CIMP. However, it is important that we provide better space savings than lossless algorithms when the accuracy is high. And it's also important that we improve the space savings that PLA algorithms provide, even when the desired accuracy is not that high. So our contribution is a novel lossy compression technique that finds the minimum number of groups we can organize PLA segments into to represent them jointly, and in this way reduce the space needed to represent PLA segments. The two core ideas of our approach are the grouping of segments with similar slopes and the use of quantized starting points for the segments. In this talk, we will discuss how our SymPiece significantly reduces the space requirements of PLA approximations. We will show that our solution is optimal in terms of always finding the minimum number of groups of segments that can be represented jointly. And we will demonstrate that our approach is very efficient in terms of execution time. But first, let us briefly discuss how angle-based PLA works. Suppose we have the 4 timestamp data values of the figure, and we want to approximate them within an error threshold. We will add points to construct segments, and while doing so, we will maintain an upper and a lower slope that are within epsilon from the values we want to approximate. The area defined by the two slopes represents all candidate lines within epsilon. As we add points, the two slopes might need to be adjusted, and the new slopes will define a new set of candidate lines. We continue while new points are within epsilon from the area between the two slopes, and we observe how the angle becomes more acute as we proceed. If a new point is not within epsilon, then we have to start a new segment. So now let's start discussing our approach. So suppose we want to approximate the signal in this figure. If we use angle-based PLA, we can come up with these segments. And our first observation here is that some of the segments have very similar slopes, which we could exploit to reduce the space requirements of the representation. To do so efficiently, however, we also want the segments to have identical starting points. So we quantize the starting point of each segment so that we come up with a limited number of discrete starting points that are within epsilon from the original value. By doing so, the 3 segments in green and the 2 segments in yellow color can be efficiently merged into 2 groups. Using quantized starting points is important because of the output we use for SymPeace, which is a list of groups that comprise the quantized value of B, the line in the middle of the upper and lower bounds of the group, and the starting point timestamps of the merged intervals of the group. So the next question is, how can we find the minimum number of groups of segments that can be represented jointly? You see, if this is the angle formed while creating a particular segment, and we have a bunch of other segments with the same starting point and overlapping angles that we want to merge, we can come up with the respective intervals, and we want to find the minimum number of groups we can merge them into. If we merge the first one from the top with the third one from the top, then we cannot merge the second one from the top with any other segment, and we end up with 3 groups in total. But if we merge the second one from the top with the third one from the top, we can group the other 3 segments together and end up with only 2 groups in total. The intersections among the different intervals can be represented even more clearly using the respective interval graph, which helps us realize that what we are looking for is the answer to a well-studied problem called minimum covering by disjoint completely connected sets, and is easily solved for interval graphs as they always have a perfect elimination scheme. And according to interval graph theory, if we simply sort the intervals in ascending order of the lower point of their interval, we can go through the intervals in this order, and if the bounds of the group we are forming overlap with the bounds of the currently considered interval, we add the interval to the group by adjusting the bounds of the group accordingly. Otherwise, we close the group and place the interval in question in a new group. If we do so, we will always come up with the minimum number of groups of segments that can be represented jointly, and our algorithm will be optimal. To evaluate our approach, we will try to answer questions with regards to space efficiency, accuracy, the impact of using additional compression algorithms, and the execution time. In this slide, we see the compression ratio of SymPeace against 4 earlier PLA approaches when setting the error at 0.5% of the signal's range for a wide range of datasets. You can see that SymPeace attains compression ratios with almost 2-fold improvement on average. Mixed is second, slide is third, and swing is fourth. These observations are also true as we vary the error threshold using larger values, up to 5% of the signal's range. Naturally, as epsilon grows, so does the compression ratio that each method achieves, but as we can see, the improvement that SymPeace offers is more or less the same. The next experiment focuses on the value of the error threshold we need to use for SymPeace and the second best approach, which is mixed, to attain better space savings than what lossless compression may offer. what we see is that SymPeace allows for using significantly smaller error thresholds, which translates to much higher accuracy. In our next experiment, we used the Z-standard algorithm to compress the PLA representations, and we report the compression ratio for both the uncompressed and the compressed representation. We see improvements for all approaches, most notably for SLIDE, that matches the performance of mixed when also using the additional Z-standard compression. However, none of the approaches is able to compete against SymPeace, despite the additional use of Z-standard. And what is more, if we use additional compression for SymPeace as well, we get equivalent improvement, so much better savings overall. With regards to execution time, we present here results for different algorithms and datasets when using an error threshold of 0.5% and 5% of the signal's range, respectively. What you should keep from this slide is that SymPeace is much faster than the second best approach in terms of space and efficiency, which is mixed. Also, it is most of the times faster than the third best approach, which is SLIDE. And finally, its performance improves as the error threshold grows, which is not the case with the other PLA approaches. And here we can see the space-time trade-off of each approach. Being closer to the bottom means that you're faster, and being closer to the right side means that you offer better compression ratio. So SymPeace clearly stands out by providing impressive space savings while also being almost equivalently efficient with the fastest approach. Mixed offers the second best compression ratio, but it's much slower than all other approaches. And Swing is the fastest approach, but the space savings that Swing offers are very modest. To conclude, SymPeace is a novel approach that exploits similarities among the line segments produced by PLA to provide a joint representation for multiple segments. In this way, we achieve significant space savings for varying values of error thresholds that are far superior than the second best approach and are calculated much faster. In the future, we also want to investigate the parallelization opportunities of our scheme. Our code is available online. Thank you for listening.